Cosmic cradles. An introduction to molecular clouds. Space is vast and often perceived as empty, but this is a misconception. The cosmos teems with activity. It is within these seemingly empty regions where we find the building blocks of stars and planets. Molecular clouds? These clouds are stellar nurseries, the birthplace of stars. Molecular clouds are cosmic laboratories where the ingredients for stars and planets coalesce. Understanding these clouds provides insights into the origins of our own solar system and countless others. By studying these clouds, we unravel the mysteries of our cosmic origins. It is a journey into the heart of star formation, where matter transforms into brilliant celestial objects. The composition of molecular clouds, a cosmic cocktail. Molecular clouds are primarily composed of gas and dust. The most abundant molecule is molecular hydrogen, also known as H2. It's the simplest molecule formed when two hydrogen atoms bond together. While molecular hydrogen dominates, these clouds are far from uniform. Helium, the second most abundant element in the universe, is also present in significant quantities. Trace amounts of other elements like carbon, oxygen, and nitrogen also exist within these clouds. These trace elements, while small in proportion, play a crucial role in the formation of planets and the building blocks of life. The deep freeze temperature and density in molecular clouds. These vast regions of space are not just visually stunning, but also hold some of the most extreme conditions known to science. Molecular clouds are incredibly cold, some of the coldest places in the universe. These clouds are often found in the darkest, most remote regions of space, far from the warmth of nearby stars. Temperatures can plummet to just a few degrees above absolute zero, around minus 270 degrees Celsius or minus 454 degrees Fahrenheit. This extreme cold is essential for the unique processes that occur within these clouds. These frigid temperatures are crucial for the formation of molecules. In such cold conditions, atoms can come together to form complex molecules, which are the building blocks of stars and planets. At higher temperatures, atoms possess too much energy to form stable bonds. The heat causes them to move too rapidly, preventing the formation of the molecules necessary for star formation. Despite their vast size, molecular clouds are incredibly dense compared to the surrounding interstellar medium. This density is what allows them to collapse under their own gravity and eventually form new stars. Density in these clouds is measured in terms of the number of hydrogen molecules per cubic centimeter. This measurement helps scientists understand the potential for star formation within a given cloud. Typical densities in molecular clouds can be thousands or even millions of times greater than the average density of interstellar space. These dense regions are the birthplaces of new stars, where the conditions are just right for gravity to take over and initiate the process of star formation. Giants in space, the size and structure of molecular clouds. These colossal formations are the birthplaces of stars and planets, playing a crucial role in the evolution of galaxies. Molecular clouds are not uniform blobs of gas and dust. Instead, they are complex and dynamic structures, constantly changing and evolving over time. They're incredibly diverse in size and structure. Some molecular clouds are relatively small, spanning just a few light years, while others are immense, stretching across hundreds of light years. Some are small and compact, while others are vast and sprawling, spanning hundreds of light years across. These differences in size and structure are influenced by various factors, including the local environment and the processes occurring within the clouds. These larger clouds, known as giant molecular clouds, or GMCs, are the true behemoths of the interstellar medium. They are the largest and most massive type of molecular cloud, often containing enough material to form thousands of stars. GMCs can contain millions of times the mass of our Sun. This immense mass is distributed unevenly, with denser regions where star formation is more likely to occur. Within these clouds, we observe intricate networks of filaments and clumps, a testament to the complex interplay of gravity, turbulence, and magnetic fields. These structures are not static. They are constantly shifting and changing as forces within the cloud interact. These filaments and clumps are the seeds of star formation, where gravity draws matter inward, eventually igniting the nuclear fusion that powers stars. The process of star formation is a delicate balance of forces, and it all begins within these fascinating molecular clouds. Section 5 are cloudy menagerie types of molecular clouds. Not all molecular clouds are created equal. They come in a variety of shapes and sizes, each with its own unique characteristics. Dark clouds are dense and opaque, effectively blocking light from background stars. They appear as dark patches against the backdrop of the Milky Way. Reflection nebulae, on the other hand, are illuminated by nearby stars. They scatter and reflect starlight, creating ethereal bluish glows. Giant molecular clouds, as their name suggests, are the largest type of molecular cloud, harboring the potential for forming entire clusters of stars. Section 6. Stellar nurseries, the birth of stars in molecular clouds. Molecular clouds are the cosmic cradles of stars. Within the cold, dense confines of these clouds, gravity reigns supreme. Over time, gravity draws matter inward, causing the cloud to collapse under its own weight. This process, known as gravitational collapse, is the first step in the birth of a star. As the cloud collapses, it fragments into smaller and smaller clumps. These clumps continue to collapse, their cores becoming increasingly hot and dense. Eventually, the core of a collapsing clump reaches temperatures and pressures high enough to ignite nuclear fusion, marking the birth of a protostar. Section 7. Peering through the veil. Observing molecular clouds. Observing molecular clouds directly can be challenging. The dense gas and dust obscure visible light, making them appear dark and opaque. To penetrate this veil, astronomers rely on other wavelengths of light, particularly infrared and radio waves. Infrared radiation can penetrate dust clouds, revealing the heat emitted by young stars forming within. Radio waves, with their longer wavelengths, can pass through even the densest regions of molecular clouds, allowing astronomers to map the distribution of molecules and study the physical conditions inside these stellar nurseries. Section 8. Famous molecular clouds, the Orion Molecular Cloud Complex. One of the most famous and well-studied molecular clouds is the Orion Molecular Cloud Complex. Located about 1,500 light-years away in the constellation Orion, this vast complex of clouds is a hotbed of star formation. Within the Orion Molecular Cloud Complex lies the Orion Nebula, a spectacular stellar nursery visible to the naked eye. The Orion Molecular Cloud Complex provides astronomers with a unique laboratory to study the intricacies of star formation in action. Observations of this region have revealed a wealth of information about the processes that govern the birth of stars and planetary systems. Section 9. The galactic ecosystem, the importance of molecular clouds. Molecular clouds are not isolated entities, they are integral components of the galactic ecosystem. They play a vital role in the cycle of stellar birth and death that drives the evolution of galaxies. Stars form within molecular clouds, and when these stars reach the end of their lives, they explode as supernovae, enriching the interstellar medium with heavy elements. These enriched materials then become incorporated into new generations of stars and planets. Molecular clouds are essential for the chemical enrichment of galaxies, providing the raw materials needed for the formation of planets and, ultimately, life itself. Section 10. Conclusion. The enduring mystery of molecular clouds. Molecular clouds are enigmatic objects shrouded in mystery and wonder. These vast, dense regions of gas and dust are the birthplaces of stars, the very cradles of stellar creation. They are the cosmic cradles where stars are born, shaping the destiny of galaxies and seeding the universe with the building blocks of planets and life. Within these clouds, the raw materials for star formation gather, creating a fertile ground for new celestial bodies. While we have learned much about these stellar nurseries, many questions remain unanswered. Despite our advancements in technology and understanding, the processes within these clouds are still not fully understood. How do these clouds form and evolve? What are the initial conditions that lead to the formation of such dense regions in the first place? What triggers the collapse of molecular clouds and the subsequent birth of stars? Is it a gradual process, or do sudden events play a significant role? What role do magnetic fields and turbulence play in the star formation process? These forces are believed to influence the dynamics within the clouds, but their exact impact is still a topic of research. these are just a few of the questions that continue to drive astronomers to peer deeper into the cosmos, seeking to unravel the mysteries of molecular clouds and the origins of stars. The quest to understand these celestial phenomena is ongoing, pushing the boundaries of our knowledge and inspiring future generations of scientists.
Like and subscribe to start your journey today.